I hope my screen is visible.
Yes, sir, visible.
Yeah. Okay. So we'll start today's session on different kinds of crack occurs in different weld locations like weld metal, base metal, heat affected zone, uh, and partially melted zones, and what are the mechanisms of those? What are the mechanisms of those crack occurring, and how can we take care or control those cracks which are occurring during the welding process, right? So this session, as you know, the this is the postponement of that Tuesday session. So so let us go through the questions then. So the first question is regarding this hot crack formation, which is mostly obvious in any kind of welding process. So this is also called, if you see this, this is also called hot cracking, is also called solidification cracking, right? Just a minute. Yeah, sorry for the inconvenience. um, yeah, so hot cracking is also called solidification cracking, as I was mentioning. So mainly this is observed frequently in, you can see in casting or any kind of ingots, which also occur in fusion wells also, right? So what are the characterization of such cracking? So these can be intergranular in nature. So this can be intergranular in nature. What does it mean? What is intergranular in nature? This is called intergranular because this is occurring along the grains or subgrain boundaries, right? So this can occur along grain or subgrain boundaries, right? What can be the other characterization? It can also occur at the what should I say, at the terminal stage of the solidification, when there is shrinkage induced trace from both weld metal solidification or some kind of thermal contraction is happening, right? And the severity of this kind of cracks increases with both the degree of constraint, if you are using some constraint or restraint on the weld, and also the thickness of the weld, right? Now coming to mechanism of hot cracking, what are the basic principle or how does it occur? The accepted theory of the solidification cracking in welds as well as casting is like coherent or interlocking some solid network separated by some continuous thin liquid films, which is kind of ruptured by tensile stresses rising from this thermal contraction. So what I was saying, that the basic mechanism, what can you say is, so there can be coherent or interlocked network separated by continuous thin liquid films that is ruptured by tensile stress, right? Why this tensile stress is arising? Because of some thermal contraction, correct? So if there is sufficient amount of liquid metal is present near the cracks when they form, they can be healed. If not, what will happen? The cracks will appear and they can be opened as tear formation, right? So for this reason, solidification cracks are also called hot tear, as I was saying. And this terminal stage of solidification refers, I already mentioned that as a characterization of that terminal stage of this solidification. What does it refer to? This refers to the point at which the fraction of solid is close to 1. So fraction of solid is close to 1, right? Rather than the point at which the temperature nears the lower limit of freezing range for an alloy. So in some alloys, depending on this nature of this fraction of solid temperature relationship, the fraction of solid can be close to this one, and essentially this complete solid network can form, and just below the liquidus temperatures, right? Now several factors favor this solidification cracking. There can be metallurgical factors, there can be mechanical factors. So in terms of metallurgical factors that increases the susceptibility of this cracking, this can include, like, there can be freezing temperature range. So there can be freezing temperature range, or there can be some presence of low melting eutectic also, or there can be uh, there can be some grain structure in fusion zone also, grain structure or subgrain structure in fusion zone, right? What else? There can be some kind of surface tension acting on the liquid metal also, right? So these are some factors which basically affect this cracking susceptibility. Now let us look at each of these factors, right? So let us try to understand what happens for each of these factors. So in general, what will happen? The wider your freezing range for an alloy is, the larger or wider the mushy zone, right? So whenever your freezing range is higher, so your mushy zone, which is liquid plus solid, that is also wider, correct? And that also affect in the area. So basically, the larger will be the area that is weak and susceptible to weld solidification cracking. So your cracking area will enhance whenever your freezing range increases. This will be more prone to crack, correct? Now, For example, the freezing range of an alloy can be increased either by some intentional addition of some elements like, let's say, zinc in aluminium, or copper in aluminium, or magnesium in aluminium, whatever. So a freezing range of an alloy can be increased either either by some intentional addition of these things, or by presence of some impurities, right? So there can be impurities like sulfur or phosphorus in steel, or some nickel based alloy maybe. So depending on those impurities, undesirable impurities, or some intentional addition of these alloying elements, your freezing range can be increased. In fact, different amounts of an intentional or unintentional solute can have different effects, right? For example, in aluminium alloys, what will happen is sensitivity to solidification cracking is greatest at intermediate levels of common solute. This is because at very low level there is very little effect on the freezing range, and mm, like little or no tendency to form cracks, since pure aluminium is restrained to cracking. Now what will happen at much higher level? So at higher level there is such a large effect, and so much liquid is present that any cracks that form are backfilled, right? And in between is the worst case. So enough eutectic liquid is there to form a continuous film at grain boundaries, and 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 like it can render the alloy crack susceptible, but not enough to backfill that incident cracks. Okay. Now in terms of this effect of impurities such as sulfur or phosphorus in steel is too, what will happen is it also uh, widen the freezing range considerably, but without producing large volume of liquids to permit that backfilling thing. So such residuals tend to segregate at grain boundaries, where uh, like diffusion rates are almost always higher due to more open nature of lattice structure. And uh, I'm not going into detail of those things, but yeah. So again if you're again some adding some impurities like sulfur or phosphorus, your freezing range will considerably enhance, right? And in these areas, these low melting compounds which are eutectic that will form, and that also lead to cracking. For example, in plain carbon steels, what happened that there can be some iron sulfide films, can produce iron sulfide films that would form and lead to severe cracking, if not for intentional addition of uh, you can add also some manganese. What will do in iron, they will form some preferential formation of globules of manganese sulfide. Okay, these are kind of harmless. So until and unless you are adding this manganese thing intentionally, if there is sulfur present, they can produce some iron sulfide thin films, and they are more prone to or susceptible to crack formation, right? And then in terms of grain structure, coarse columnar grains, as you are already aware of, coarse columnar grains are more susceptible to solidification cracking than these fine eqx grains, right? Why they are more susceptible? There can be several reasons. So let me climb this up. So as I was saying, coarse columnar grains are more susceptible to cracking compared to fine equexed grains, right? Now, first first thing is like fine equals grains can better deform to accommodate these contraction stresses, right? Or relieving stresses across these interdendritic boundaries. And secondly, liquid can be more effectively fed to these incipient cracks to promote healing in fine grained materials, where these grain boundaries run in all directions, right? Thirdly, when grain boundaries are greater, when grain boundaries are greater, the concentration of potentially harmful low melting point segregates are reduced, hopefully to below some threshold that causes cracking. And beside these effects, there ca- beside these effects, this head-on impingement of columnar dendrites growing from opposite sides of a weld can lead to severe centerline segregation, right? And yeah, these are particular problem in austenitic stainless steel, austenitic stainless steels, what I was mentioning. uh, it is not just the presence and amount of this low melting phase or segregate that leads to solidification hot cracking. It is also, as I mentioned, the surface tension of the liquid. So if the surface tension is between the solid grain and the grain boundary liquid is very low, a thin liquid film forms by wetting the grain boundaries, right? And for this situation, the susceptibility to cracking is very great, is to higher extent. And on the other hand, if surface tension of liquid is high, it will tend to ball up to form some globules and will not coat the grain boundaries with a continuous film, right? So this basically reduces this susceptibility to cracking. And these effects of different surface tension on liquid, uh, yeah. So there can be some mechanical point of views also. Those were some metallurgical factors. So in terms of mechanical factors, what can be the different mechanisms for this crack formation? So there can be this contraction stresses. One is this contraction stresses, and another is degree of restraint, right? Am I audible? Am I audible?
No, sir.
Yeah. Okay. So as I was saying, there are two different factors. One is this contraction stresses and degree of restraint. Uh, so in terms of contraction stresses, what can we say? So far these metallurgical factors of this weld solidification cracking, uh, I just explained. But without presence of these traces acting on these adjacent grains during solidification, no cracking can occur. So such traces, as already mentioned, can be due to some thermal contraction or solidification shrinkage, or both can be there, right? Now, if you think of these austenitic stainless steels, they have relatively high thermal expansion coefficient, and therefore they are often more prone to solidification cracking. And in aluminum alloys, they have both high thermal expansion coefficient and high solidification shrinkage, and as a result, solidification cracking can be rather serious in some aluminum alloys. Okay. Now, in terms of degree of restraint, what will happen? The degree of restraint of the workpiece is another mechanical factor, right? So, for the same joint design and material, uh, the greater is the restraint of the workpiece, they will be more likely to solidification cracking, right? So, yeah. So in terms of remedies, can there be any factors which can control this hot cracking formation? So yes, solidification cracking can be minimized by knowing where it is coming from, and like there are three basic approaches. So either you can control the composition of the weld metal. So one is this controlling the composition of the weld metal, or you can control the solidification structure, or else you can do the weld under some favorable conditions. Okay, welding under favorable conditions. So should I go into depth? Okay, okay. Let us discuss something. Uh, so in terms of this control of this weld metal composition, now what is autogeneous welding? Any idea?
Without using filler metal, we can do weldings.
Right. So in autogeneous welding, when there is no filler metal is used, so weld metal composition is determined by the composition of the base metal itself, right? To a much lesser extent, the composition of the shielding atmosphere, which would affect that extent of oxidation and thus loss of certain alloying elements. So to effectively avoid or reduce the solidification cracking in autogeneous welding, uh, oh, so basically, what should we do? We should basically avoid the base metal composition that are prone to cracking, right? And when filler metals are used, the weld composition is essentially controlled by the composition of base metal, the composition of filler metals, the dilution ratio, and so those basically can affected to a lesser extent by the composition of the shielding flux or gas. So the dilution ratio is basically the amount of base metal whatever is melting and that dissolved to the total amount of metal in the fusion zone, right? So this dilution ratio can vary significantly from one type of joint to another. So joint design as well as the welding process and procedure that should be carefully selected, right? uh, yeah. Now this filler metal composition, this flux or shielding gas process, operating parameters, welding procedures, uh, including this prevention of dilution, those must all be carefully considered and selected to control this weld metal composition to minimize this solidification cracking. So in let us understand in terms of some examples, uh, like copper in aluminum alloy can be used to control the freezing range and amount of this eutectic liquid. And you can also use some residual element contents such as sulfur and phosphorus in steels or nickel based alloys. Then there can be some manganese content in steels to control the distribution of these low melting segregates, as I was mentioning, such as iron sulfide. Then also you can use some alloy content to control the fusion zone structure, uh, also to control the carbon level in steel to keep it some low range to avoid the martensitic formation. Those things are coming into picture, right? And then in terms of controlling the solidification structure, uh, how can we control the solidification structure? uh, like there can be a way to reduce this incidence of solidification cracking is to like basically you can control or Like you are well aware of this G by R ratio, right? Solidification rate and thermal gradient thing. And you can basically play with this G by R ratio or and the GR product. So depending on your cooling rate, those grain structures can vary. Depending on your solidification structure, your metal would be either susceptible to cracking or not, right? So almost without exception, control of the structure means attempting to minimize the grain size, correct? Now by reducing the grain size, what we are doing, any potentially detrimental, like detrimental microsegregation or some low melting phase or constituent is uh, basically spreading across the more grain boundary areas, and that might reduce the level of segregate to below some threshold level, and which can cause this continuous liquid formation and thereby preventing the cracking. Okay. And in terms of this favorable welding condition, what I mean to say is like you can employ some high intensity, high energy density or low heat input process, like some laser beam welding or electron beam welding, right? So those are high intensity process where heat affected zone will be, you can control the heat affected zone, the low heat input process there, right? Or else you can minimize the restraints also, or else you can preheat the material to reduce the stress and cooling rate for materials that form these inherently brittle phases, right? Or else you can control the weld profile and bend shapes also. So those are some of the things which can be controlled to control the uh, weld metal solidification cracking or hot tear formation, whatever you can say. So yeah, coming to the questions, which of the statement are correct for the hot cracks? Now, it occurs in the weld bit only. No, it doesn't occur only in the weld bill. So it can also occur in heat affected zone, right? So this is not correct. So when it occurs in weld metal, it is called solidification crack, and when it occurs in heat affected zone, it is called liquefaction crack, right? So statement 2 and 3 are correct here. Agreed? Okay. So mm, yeah, we'll move to the next question. So here it says, in weld metal zone of steel, magnetic transformation, and we have some of the options. Now, in terms of this conventional hot cracking, or you can also think of this liquefaction cracking in this heat affected zone. So the alloys can suffer from several problems basically. One is this hot cracking, another is of course this liquefaction cracking. Then there can be loss of ductility, which is the point of concern for this question. And then there can be some kind of hydrogen cracking also, right? Now, how this loss of ductility is happening? So if you see, many eutectics are inherently hard and brittle, right? So many eutectics are inherently hard and brittle, and thus this lower the ductility of a material, right? So the reason for this is twofold. Like, first is in binary system, if you see, eutectics always consist of an intimate mechanical mixture of two phases, right? So what are those eutectics? They are intimate mechanical mixture of two phases, right? So one of which is often much stronger and harder and more brittle than the other, right? And the result, of course, is that you are getting some weaker, softer, but tougher phase is strengthened and hardened, right? And however, the resulting two-phase mixture or constituent is also made less tough and less ductile. And second is that the interface between these two phases is extensive, right? So often in the form of some alternating layers in what are called some lamellar eutectics. So the large shared interface between an inherently tough phase and an inherently brittle phase. So what they do, they inevitably limits the toughness of the combination. Correct. So the reason is that for loading along or parallel to that lamella, this lamellar eutectic, the maximum strain that can be tolerated is limited by the less ductile phase, right? And it should come as no surprise then that once extensive segregation of a eutectic constituent to grain boundaries occurs, so the ductility of that solidification structure is lowered considerably, right? So this problem can be made worse by the fact that to reduce this embrittling effect means removing or drastically altering the structure of the eutectic. So you have to do that. The only way to do this is by heat treatment, correct? So unfortunately, what happens is like redissolving an eutectic requires some temperatures that are well beyond what is normally considered reasonable for post-weld heat treatment, and that is into the solutionizing range where a single phase solid solution is formed above some solver's temperature. Another option can be, of course, is to attempt to modify the structure of a lamellar eutectic, and how that can be done is like you can do some long time soaking at elevated temperatures, and basically some second phase particle will form in some spherical structure within the matrix of that first phase. And so what you are doing is basically you are driving the force for this is the reduction of this interface energy, right? And the process is called spheroidization. So you can do some spheroidization and modify the eutectic structure, do some heat treatment to solve this problem, right? Yeah. So coming to the question, it says that martensitic transformation has adverse effect on the weld cracking tendency. Yes, and this is false. Of course not. So your martensitic structure is too much brittle and prone to crack, right? So only option one is correct. Okay. So moving to the next question, which of the following is not type of cracks generated during welding? So we will spend some time in understanding these different kinds of cracks. That would be better. Otherwise the question is very straightforward. Like you're well aware of that. chevron cracks can be formed, lamellar cracks can form, reheat cracks can form, and there is some entangled cracks which is not a type of cracks generated during welding. So these are the four types of cracks which can be generated during welding. Now, in terms of chevron cracks, what are those? So they are kind of old metal cracks. Also they are known as staircase crack, right? So this is also known as staircase crack. And why that? Because these can occur at 45 degree to the world axis, right? So if you see, these kind of cracks are kind of intergranular and transgranular cracks, usually associated with some submerged arc welding fluxes and sometimes also with some coated electrodes. Okay, so mostly these are intergranular and transgranular in nature, and they are of course the hot cracks actually, and caused when metal is subjected to some ductility deep cracking, as steel may lose ductility between some what should I say, in between some 1200 degrees C and more than that, and that can be recovered at about 800 degrees C. And as I was saying, if there is presence of this sulfur and phosphorus at grain boundaries, that time also you will have this loss of ductility, right? So in general, if you see, these chevron cracks are formed like if you are having this. Let's say this is your weld metal surface. So this is my welding region. So in the welding region, they can form like 45-degree. This is my welding axis. So these kind of cracks can look like this, right? Now you have these lamellar cracks, then you have reheat crack, then you have this stress corrosion crack, and also you can have this hydrogen cold cracking also, correct? So we'll try to understand one by one, not in very much detail. And yeah, also there can be some liquefaction cracking happen in heat affected zone, right? I already mentioned that. So okay, we'll try to understand one by one. Now this liquefaction cracking, what is happening is by this phenomenon, melting can occur even where the peak temperature of the local weld thermal cycle is less than the equilibrium solidus, right? And hence supporting that the phenomena can occur in heat affected zone also. So obviously in heat affected zone, melting does not occur. It does not go to the actual melting temperature of the base metal, but somehow it happens that the peak temperature of the local weld thermal cycle is less than the equilibrium solidus and melting is happening, right? Why this is? Because of some constitutional equation occurring during this non-equilibrium heating, and there can be some development of some solid gradient around the second phase particles into the matrix phase, which leads to melting of the eutectic temperature and at eutectic temperature, right? And even though the nominal alloy composition lies in the single phase terminal solid solution region, right? So yeah, So tensile stress induced by this volumetric shrinkage as liquid transformed to solid in fusion zone, along with this non-uniform thermal contraction in the heat affected zone, uh, that can act on this constitutionally liquid film surrounding these second phase particles and in grain boundaries to produce these hot cracks, which are called, we call that as liquefaction crack. Now, this liquefaction cracking is seen to occur in the high temperature region, uh, in high temperature region of heat affected zone. Like you can see it in different kinds of steel also, like austenitic stainless steel, heat treatable steel, and also in aluminum and nickel based alloys also. So these kind of cracking can be particularly, what should I say, dramatic in heat effector zone of cast irons. So formation of this whenever there will be formation of this iron carbon eutectic ledeburite, no, so you can have this iron carbon eutectic ledeburite formation at 4.3% of carbon, that leads to this liquefaction cracking if the condition is, if your heat input or preheat or both the things are too much high. So such conditions is basically being employed to prevent the formation of brittle martensite also. So what can you do to overcome liquefaction cracking in such cast irons is there is some technique called quench welding. So that can be used in which several smaller stringer beads are made intermittent. In some intermittently, the stringers beads can be made without preheat so as to maintain the interface temperature below some, let's say 100 degrees C, right? And these kind of cracking tends to exhibit an intergranular mode, of course. They are always seen along the grain boundaries that many second phase particles precipitate preferentially and constitutionally liquid, and those can be spreaded out to produce this continuous or discontinuous grain boundary films, right? Now coming to this reheat or this is also called strain edge cracking. This is also called strain edge crack. Now what will happen during reheat or this strain edge cracking? This kind of cracking is found mostly during this post weld heat treatment, correct? So during this post weld heat treatment of some certain alloys, most notably you can see nickel based alloys. During this post weld heat treatment, this kind of cracks can form, and the purpose of such post weld heat treatment is like twofold. One is you want to relieve this weld induced residual stress, right? That's why you do this post weld heat treatment. And what else, you can develop some maximum strength by aging also. So to age this weldment, what you need to do is you must first solutionize the thing and then quench it, right? And then you do the aging process. So during solutionizing, your residual stress in the weldment are relieved, of course. And however, it is quite possible that for some aging to occur in regions of this heat affected zone that were solutionized by this heat of welding, and since aging occurs at lower temperature than the stress relief, right? So when this is the case, so cracking can occur as the alloy in this region age hardens or becomes stronger but less ductile, and basically that is acted upon by stress to cause cracking, right? And this phenomena is called strain edge cracking or simply reheat cracking. So in terms of mechanism, let me draw a figure. So here you have time, here you have temperature. So this is my this is my welding process where there is increase in temperature, and then you are doing cooling, and during the post welding treatment what you are doing is, so here you will have some residual stress generated, and then you are doing some post weld heat treatment, you are doing some heating and then solutionizing the thing, and then you are cooling and then doing some aging and then again cooling, right? Here you are solutionizing the thing, and there can be aging temperature range here, correct? Now, so reheat cracks usually initiate in the heat affected zone, but not always, of course, and propagate intergranularly into that region unaffected by that welding heat, right? In fact, several mechanisms have been proposed for this low ductility in heat affected zone, leading to this strain edge cracking or reheat cracking. Like there is some mechanism called embrittlement embrittlement of grain boundaries due to either liquefaction or solid state reaction. Anything can happen during welding. Then embrittlement of grain boundaries, there can be oxidation during heat treatment also, and then there is some kind of change in deformation mode from transgranular slip to grain boundary sliding. So those are some mechanisms have been proposed for this reheat cracking, right? And then you have this one more thing is there is lamellar tearing, right? So lamellar cracks also form, most notably in kind like in wrought iron or some kind of mild or low alloy steels with some non-metallic inclusion. They can exhibit lamellar tearing. And what is happening in lamellar tearing is this is some result of a combination of some highly localized stress due to weld construction and some low ductility of that base metal in its throw thickness reduction parallel to the rolling direction, right? So due to the presence of these elongated stringers of non-metallic inclusions, so this tearing is basically triggering by some decohesion of these inclusions, or uh, like there can be silicates or sulfides. So those inclusion always can uh, basically, they're acting as a decohesion thing, right? And the problem is particularly severe just outside the fusion or partially melted zone. And there are ways, of course, to avoid this lamellar tearing. So basically you can employ some for uh, so lamellar tearing. So in terms of lamellar tearing, as I was saying, uh, there are some ways to avoid this lamellar tearing. Is one is, of course, employing some joint design that can cause these contraction stresses to act along rather than across the rolling direction of susceptible materials, right? So employing joint design that cause contraction stresses to act along rather than across the rolling direction. And one more option can be grinding or machining away the volume of the workpiece where the steering is anticipated, right? So grinding or machining away the volume of workpiece where steering is anticipated. Okay. Okay. So lot of discussions happening today. We'll move to the next question. This I already mentioned that chevron cracks occur in 45-degree to the welding directions, right? So option one is correct here. Okay. So which of the statements are correct for the crater cracks? Now, what is a crater crack in welding? Crater crack is basically a type of welding defect that can occur when the weld pool cools too quickly. So this can happen if the welder doesn't have enough heat going into the weld, or if there is too much, let's say there is too much wind blowing into the weld pool. So basically, the basic thing is if your weld pool is cooling too quickly, at that time crater crack can happen, and this can also occur if the welder is moving too fast. The welding speed is so high and it doesn't allow enough time for the weld to properly cool, right? So yeah, so crater cracks can also occur as I was saying the welder is moving uh, the electrode too fast. Your welding speed is too high and it doesn't allow enough time for the weld to properly cool before you're moving on, right? And these kind of cracks can be dangerous because they can create some weak point in the weld which can lead to failure. And like if you suspect that your weld has a crater crack, it's important to have it inspected by some qualified welding inspector. Or like crater cracks can usually be repaired by some re-welding the affected area. Or like it's important to make sure that your root cause of the problem is addressed. Those things are important in any kind of crack formation, of course. And there are few different factors that can contribute to this crater crack in welding. What are those? One of the most common causes welding. You are doing welding too fast, right? Welding speed. If your welding speed is very high, welding speed is very high. So that doesn't allow, as we are saying, enough time for the weld pool to cool properly, and that can cause the weld to crack as it solidifies. And another common cause of the crack. crater is too much heat. That is also not ideal for a welding. So these are the reason of crater crack formation. Okay. So uh, what I was saying, too much heat. So this can happen if whoever is doing the welding, that he doesn't have enough the welding doesn't have enough power, or if there are other factors that prevent proper heat transfer, right? And how can I stop my crater cracks from welding? So one of the most important thing is to make sure that you have enough power going into the weld. And if you're using some arc welding, this means making sure that amperage is high enough, right? And you also need to make sure that you're not welding too fast, and this can be a difficult balance to strike, but it's important to find the right speed for your weld so that the pool has time to cool properly. Yeah, that's it. So in terms of the coming to this question, uh which of the statements are correct for this crater crack? These are not usually t-shaped, so this is a false statement. And yes, these are tiny cracks that appear at the end of the weld when where the arc has been broken, and it is generally found in steel having a higher coefficient of thermal expansion. Sure. So option 2 and 3 are correct. Any questions till now? So till now we have covered this hot crack formation, the mechanism of hot crack formation, what can be the remedies to remove those hot crack formation, and how this loss of ductility can affect your weld microstructure, and why these martensitic transformations is not good enough for your welding, and that can lead to crack formation. And we have also discussed different kinds of cracks like chevron, lamellar, reheat, stress corrosion cracks, and then you have this crater crack formation, right? So if there is no question, we'll move to the next question then. Yeah. So this is something from this underbead and toe cracks in heat affected zone of steel is due to there are some reasons, and we need to find out the correct option. So in terms of this question, let us try to understand this hydrogen cracking in more depth. we have not spent time on hydrogen cracking till now. So what is happening is like huh. So there can be some various sources of hydrogen during welding, right? So the hydrogen levels in welds made with various welding process and solubility of hydrogen in steels, the method for measuring weld hydrogen content, those are theirs. Okay, so mm, I'm a little bit confused. How should I uh, explain the thing, or in what terms? Like, okay, let us initially understand the mechanism. Let us initially understand the mechanism, how this hydrogen cracking happens in welding. So hydrogen cracking basically occurs when there are factors like factors like not AB. So there can be hydrogen in weld matter. There can be high stresses. There can be susceptible microstructure like martensite formation. And yeah, so high stresses can be induced during cooling by solidification, shrinkage, and some thermal contraction, right? Under constraints, right? And martensite is especially hard and brittle high carbon martensite is susceptible to hydrogen cracking always. So martensite formation temperature is relatively low, and hydrogen cracking tends to occur at relatively low temperatures, right? So for this reason, it is often called cold cracking, or also sometimes called delayed cracking, due to this incubation time required for crack development in some cases. So okay, let us let us try to draw some schematic here. So let's say you have this. This is my weld pool. Okay, this is my weld pool. Of course, this is my electrode, and you have this arc formation. And then let's say let's say this is my weld pool, and here you have this. Let's say you have this crack formation here, and there can be introduction of hydrogen over there, can form some martensite here. Okay, so hydrogen is from here. So basically, this figure depicts the diffusion of hydrogen from the weld metal to the heat affected zone. Okay, during welding. And yeah, so this mechanism of this hydrogen cracking is still not clearly understood somehow, and there are numerous theories have been proposed, and it is not intended here to discuss these theories, since there is uh, yeah. And how does it appear is basically like there is typically this form of hydrogen cracking is called something called underbit crack. This you are well aware of, underbit crack, and this is essentially parallel to this fusion boundary. This underbit crack is parallel to fusion boundary, and this is caused because of stress concentration, and also there can be something called toe crack, right? So if you are having some fillet weld like this, if you are having some fillet weld like this, so this is my fillet weld, right? So underbit crack happens at some vicinity of that fillet weld, where there can be crack formation in the vicinity of this uh, fillet weld, which is called underbit. And if it is happening at the toe location, that is called toe cracking, right? Now coming to this question, underbit and toe cracks in heat affected zone of the steel is due to, of course, this is not due to low hydrogen retention capacity, because if your hydrogen is high enough, then only this kind of crack formation is occurring. And it says relatively high carbon or alloy content in steel. This is the true statement. So if you are having, as I was saying, for martensitic formation, you are having some relatively high carbon content in steel, right? And that can cause this an underbead and toe crack formation. And martensite can form only because of fast cooling rate. So this is also a false statement. So here only option 2 is correct. So here we have option 2 is correct. Okay. Hmm. So here it says which of the factors does not increase the reheat crack susceptibility. So I have already discussed the formation of reheat cracks. Okay, let us try to understand in some different ways. So here, as I mentioned, reheat crack is kind of some well recognized problem, of course, in some low alloy ferritic steel that contains some chromium, molybdenum, or sometimes there can be vanadium, tungsten to enhance those corrosion resistance uh, and elevated temperature strength. Now, this alloy steel sometimes also called some creep resistant ferritic steels and frequently used for this elevated temperature service. Anyhow, uh, these creep resistant ferritic steels are reheated often to about, say, let's say some 500 to 600 degrees C after welding to relieve those residual stresses and hence reduce susceptibility to hydrogen cracking or stress corrosion cracking, right? However, cracking can occur in heat affected zone during reheating, right? So examples of ferritic steels which are susceptible to this reheat cracking, so that can include, let's say, you have this alloy formation, or else there can be 50% chromium, molybdenum, vanadium, or else there can be chromium, like this alloy formations. Okay, and some researchers have proposed a formula for this effect of alloying elements on this crack susceptibility for this reheat cracking. So this is crack susceptibility, which is telling like that is equal to percentage of chromium plus 3.3 into percentage of molybdenum, then your 8.1 into percentage of vanadium, that minus 2. So when this value of crack susceptibility is equal to or greater than 0, the steel may be susceptible to reheat cracking, right? And then in terms of causes, what caused this reheat cracking, the mechanism of reheat cracking, like during welding, the heat affected zone near this fusion line is heated to temperatures very high in the austenitic phase field, right? Where these pre-existing carbides of chromium or molybdenum or vanadium dissolved and some austenites grains grow, right? And subsequent rapid cooling does not allow enough time for carbides to reprecipitate, and those things result in supersaturation of these alloying elements, and like basically austenite can transform to martensite if hardenability is sufficient, right? And when the coarse grained heat affected zone is reheated to elevated temperature for stress relieving, what will happen is fine carbide precipitates at like those fine carbide precipitate at dislocations in the prior austenitic grain interior, right? And those also can strengthen them before stresses are relieved. So what is happening is the grain interiors are strengthened, grain interiors are strengthened more than the grain boundaries, right? And since this occurs before stresses are relieved, cracking can occur along the grain boundaries. So the reheat cracking susceptibility can be evaluated by measuring the extent of crack growth. So there are some what should I say, some standard experiments, like you can do some compact tension specimen or some Sharpie V0 specimen, which is loaded and kept at the reheat temperatures around 600 degrees C, and uh, you can do some taste, like you can do some taste, like the specimens are made by welding two pieces of, let's say, 50 thick plates together, and the ends of these test specimens are welded to a stainless steel block. And upon reheating, the test specimens are subjected to tensile loading, correct? And that is caused by the higher thermal expansion coefficient of that stainless steel. And then basically you use some formula that can determine the overall strain in the test specimen, and that's how you find out that whether what is the extent of that reheat cracking, right? And as I already mentioned, in terms of remedies, uh, what you can do for controlling those reheat cracking is like you can do some multipurpose welding. So multipurpose welding is basically induce some preheating thing. So uh, whenever you are doing some preheating, the susceptibility to crack formation will automatically reduce, right? So here for this question, which of the factors does not increase the reheat crack susceptibility? Structure with poor ductility, it increases the reheat crack susceptibility. Higher heat input, it also increases the crack susceptibility. And then preheating, it also increases the crack susceptibility. So only you have this fine grained structure, it does not increase the reheat crack susceptibility. So as I was mentioning that you can basically do some multi-pass welding. So uh, to control this reheat cracking, what will happen with a single pass weld procedure? The grains are coarse, right? And during reheating, as I was mentioning, there can be this fine carbide precipitation, a dislocation in the grain interior. And meanwhile, those coarse carbides can also form at the grain boundaries also. And it basically deplete the adjacent region of carbide forming alloy element. And these can cause a precipitation free zone to form along the grain boundaries, right? Okay. So this is a match of the followings where there are different kinds of crack formation like lamellar, chevron, stress, corrosion, toe cracks, and there are different location of the weld metal, not the weld metal, the welding region. So which cracks can form at which region? We need to match those followings, right? So here, if you see, lamellar cracks is mainly located in heat affected zone. Chevron cracks is mainly located in weld metal. Then you have stress corrosion cracks, which are located both in weld metal and heat affected zone. And then you have toe cracks, which is located on plate surface. Uh, there is nothing to discuss as such in terms of uh, for this question specifically. Any questions till now? We have two more questions. We have two more questions. Okay. So if we have no question, we'll wrap it. We'll wrap this up quickly, as I have explained the things already. As I have explained the things already. So here it says, which of the following methods can be used to prevent the occurrence of lamellar tearing in the weld? So what is happening during lamellar tearing? So in brief, I already mentioned lamellar tearing. What is that? In brief, if we say, that is the combination of high localized stresses due to this weld contraction and low ductility of that base metal, right? In the through thickness direction due to the presence of some elongated stringer of the non-metallic inclusions, right? And tearing is basically triggering by that decohesion of such non-metallic inclusions, right? Usually you can have some silicates or sulfides like that, right? So uh, coming to the question, Which of the following methods can be used to prevent occurrence of lamellar tearing in weld? No, no. Use of steel with high sulfur content is not a correct option. So either you can have this reduction of hydrogen content, or else you can treat your steel with some rare earth metal. So option 2 and 3 are correct here. Excluding these things, a practical way of avoiding lamellar tearing is to employ some joint design that allow the contraction stresses to act more in rolling direction, right, of the susceptible material and less in transfer direction, which is the through thickness direction. Correct. As I was saying. So excluding this thing, so you can employing a joint design that allow contraction stresses to act more in rolling direction of susceptible material and less in transverse, which is the through thickness direction. Okay. Yeah. So this is the last questions for today's session. Which of the statements are correct for lamellar cracks? So it occurs in the heat affected zone due to a combination of localized stress and low ductility of the metal in the through thickness direction. Yes, this is true. The crack appears to be closely associated with the age of the heat affected zone. This is also true. This is also true. And as I was saying, crack initiation occurs because of the decohesion of this non-metallic inclusion. So all of the three are true. Okay. Any questions on today's session? If there is no question, we'll finish the things here. We'll meet next Tuesday. Yeah, we'll meet next Tuesday. Bye bye. Have a good day.
Thank you.